Hello. In this discussion, we're going to be continuing our discussion on vectors, more specifically something called the dot product. So it's a new operation. So let's begin with the definition of what the dot product is. So if you have two vectors, v and w, and they give them to you as a linear combination on both, so it's a1i plus b2j, and remember you can write this in component form as well, and vector w, which is a2i plus b2j. And these are two vectors. Now the dot product with v dot w is like, it looks like a multiplication. So it's not a simple multiplication. You don't just multiply the x components and multiply the y components and get the answer. That's not what it is. Because when you get the dot product, the result, pay close attention to this, the result is a scalar. If you remember now, when you add two vectors, the result was a vector. When you subtracted two vectors, the result was a vector. When you multiplied a scalar times a vector, the result was a vector. But the dot product doesn't give you a vector. It gives you a number. It gives you a real number, or we just call it in vector terminology a scalar. It's a scalar. So what you do when you do the dot product, v and w, you multiply their x components, you multiply their y components, and then you add the numbers together. Now this has a lot more reason to know this in future classes like Calc 2. So Calc 2, maybe Calc 3 even. This course, not so much. I wanted to introduce it here so it wouldn't be a totally new concept for you, for those who have to go on to Calc 1, Calc 2, and Calc 3. And so I wanted to put it here. Okay? But the dot product is not a vector. It's just a number. It's very easy to do. It's a very easy concept. But it's just a lot of people want to do the dot product and get a vector, and it's not the way it is. All right? So let's look at a series of examples here. We have a vector v, which is negative 3i plus 4j, and vector w, which is 2i minus 5j. So we're going to do the dot product of a series of these vectors, and then we're going to, only in f, we're going to find the magnitude of them. So we're going to find the dot product of v times w. So let's look at that. So vector v times w, dot product. So it's going to be a negative 3 times 2, multiply their x components, and then 4 times negative 5, multiply the y components, and then just figure it out. Negative 3 times 2 is negative 6, and 4 times negative 5 is negative 20, and then it combines to negative 26. Okay? Now we're going to note the result of this. It's going to be a little bit more important in a second, but right now, just the number accepted, it's a negative 26. What it isn't is more telling. Now, you'll understand later. It's not 0, okay, which means the vectors are not something else. So I'll talk about that when we get to it, okay? So the dot product is a negative 26. Now, part B, w times v, multiplying the other direction. So it's going to be 2 times negative 3, and then negative 5 times 4, and so it's a negative 6, negative 20, negative 26. What does it appear? It appears that the dot product is commutative. At least it does on this one. And I believe the dot product is commutative. All righty? And then vector v times v. Vector v times dot product applied to itself. So it's a negative 3 times negative 3. And then 4 times 4, because that's the y component. And so negative 3 times negative 3 is 9. 4 times 4 is 16. So it's 25. Now what about w times w? Well, the x component is 2, so it's 2 times 2. The y component is negative 5, so it's negative 5 times negative 5. So 2 times 2 is 4. 5 times 5, negative 5 times negative 5 is 25, which gives me 29. So right now, that's just what the dot product is. So you know how to do it. Now notice all the results. The negative 26s, the 25, the 29, they're scalars. They are not vectors. Okay? Now, the E and the F we've done before. This is just kind of a rehash of something that we will need to know this in a bit. But for right now, you already know how to do the magnitude of V. Remember, it's the square root of A1 squared plus B1 squared. So it's going to be a negative 3 squared plus 4 squared. 9 plus 16 is 25. And the square root of 25 is 5. Okay? Now the W. 2 squared plus a negative 5 squared. Square root of that is 4 plus 25, which is the square root of 29. Now I want you to notice something there. Look at E and F. Look at C and D. Okay? Look at C. Look at the answer to C. C is 25. E is the square root of 25, which is 5. D is 29. F is the square root of 29. Do you see a relationship there? One is the square root of the other. So there is a relationship there. If you square the magnitude, you get the dot product of the same thing. So in other words, the magnitude of W squared is equals to the dot product of W times W, which is pretty cool. Okay? And I believe we discussed at the very bottom down there. So yeah, if U, V, and W are vectors, the commutative property applies. We've already talked about that. Vector U, we have vector U times vector V is vector V times vector U. So the dot products are commutative. Let's go back to see it again. Look at the answer to A. Look at the answer to B. Look at the answer to those. It's the same thing either way you go. Now, the distributive property is also going to apply. The dot product of U times the sum of two vectors is the same thing as the dot product applied to the first one plus the dot product applied to the second vector. Now that one we didn't really discuss, but it is true. And then what I just talked about a while ago, if you square the magnitude, that is equals to the dot product of V times V. All right? Or if you want to use W's instead, that's fine too. W dot product applied to W is going to be the magnitude of W squared. So it doesn't matter what's the name of the vector. And then 0 vector times the dot product of V is 0. Alrighty? Which is very easily proven. Alrighty? So that concludes the dot product discussion. We're going to use a little bit, we're going to need to use that a little bit more in some upcoming discussions as well. So this is something you can't forget. Now, like I've always said, when you get to a point like this, when you have a table, good places to pause and then write it down in your notes so you'll be able to use it. And other than that, we're done with this discussion. And if you have any questions, you let me know, and you have a good day.